Hi there, I'm Mago, and finally my operating system can print out some text. How we got there? If you remember last video, I told, okay, I will work on the std out. It's not really std out, but it's pretty close to it, and more importantly, I can use it to debug operating system while on hardware, like on real hardware, using the serial output of Raspberry Pi. Like it's just a standard thing that you used to use in Arduino thing. It's a UART interface. In the last video, I used to follow the tutorials from the blog of Opperman about the development of OS on Rust. But unfortunately, the next step of this video was about preparing this kernel for x86 architecture, not really ARM architecture that I trying to implement for it. I'm not really sure why Opperman in the first blog post makes standalone version for ARM architecture and then switch to the x86 architecture. But I had to switch to another tutorial that I found in the GitHub. There's a repository called Raspberry Pi OS development. I will leave the link below. It's basically what I really need and what I pursue, so what I want to do. And I started to do this using this tutorial. The first step was, according to the new tutorial, reorganize the project so we have separated models, crates, as you call in Rust, crates to care about different parts of the operating system. So we have part that cares about memory, we have panic handler, we have CPU code, and the thing calls BSP, like board specific packages. And this tutorial proposes architecture of the operating system where we have a general kernel separated from the board specific code. And board specific functions exposed using the interface. So you have the same interface, but it can have different underlying implementation depending on the board. Let's say we can develop, we'll have the same operating system which can run on the both boards, like Raspberry Pi 3 and 4, which have different hardware implementations, and we can implement different parts in these BSP packages and expose them using a single trait interface, which will be later used in the general kernel. Other important part was emulation. You don't want really every time when you're changing something, upload the code to the hardware and testing it on the hardware, because you don't have necessary tooling to see what's going on. The same tutorial proposed to use QEMU. It's a universal emulator where we emulate the real hardware that we're planning to use on our host machine. In my case, it's a Mac OS, and QEMU emulates basically the ARM architecture for me, so I can test it and have real world experience of running my operating system on real hardware. To use QEMU, this tutorial introduces a makefile that basically cares about whole process of building, compiling the code, putting this into the certain place, and running QEMU using this image. It's a complicated and scary looking makefile from the first look, but I really suggest you, if you're interested, to dig into it and give it a look, change a bit, try it out. This way you'll understand it better. Exactly what I did, I tried to not just copy paste the code, but I tried to edit some parts. For example, I removed documentation and then it's failed, and again. And also it works mostly with a 9th version of the Rust compiler. With stable it doesn't work because some features doesn't exist there, and so on and so on. It's really a thing that you need to care about. You need to look into it and try to understand by yourself. It's not just a copy-paste thing. Again, if you want to follow the whole project and do this similar thing, I suggest really go through the code step by step, try to understand this. And now I will give you a short explanation how the code works, and give you a rough picture like how the project works at all. Let's start from the very beginning. When we make QEMU, it will follow according to the make file. We'll compile the code and upload into the emulator, and when it's running, the starting point won't be that same starting point that we wrote on the last video. It will be a different one. Starting point redefined using assembler that lies in the _arch folder where is a boot.rs, and it loads boot.s file, where basically with assembler code defined which function will be a main function of this operating system. Then it passes the control to the Rust. So it defines assembler starting point, and then it passes to the Rust starting point. This function in its turn calls the runtime init function, which finds itself in the root directory in runtime _init rs file. On its turn, runtime init function zeroes out a block starting symbol section and passes to the kernel init function. And this is the function where we do stuff. So basically this will be a point where we run any commands and do our computation. And as you can see, here's just a printout thing, and I will explain next how the printout thing works. But before we start, I think the whole thing is pretty complicated, and I do myself understand like about 50% how everything works here. So I had to dig into the little bit assembler code and try to follow this. And if you want to understand this as well, at least 50% as I do, I suggest you to follow step by step each function that calls and read the comments that comes with the code in this tutorial. They're very helpful and a little bit refresh your knowledge or learn again the assembler thing, because it gives you understanding how it works. You need to understand it's like a hardware specific code that boot.s is really a hardware specific thing. If we will rewrite the code for other architecture or other CPU or other things, so we will need to rewrite this assembler part completely and maybe partially Rust part for new CPU, because it's a lot to do with hard-coded address, memory addresses, register address, and so on. So it's tied to the hardware. So it needs a knowledge about hardware as well. So let's get into the printing things. So basically we introduce console trait, and in this again in the board specific packages we have the console.rs as well, where we introduce new structure QEMU output, and for this structure we implement function write. And if you look into this write function, you see this function write byte by byte writes into the hard-coded address in the memory. It's a register of UART on this particular board, and then we expose this write function as a console like public function, and then in the root directory we have the file like print.rs. And this file makes use of this console function, introducing two macroses. So one is the print and another is println, basically ln like from the next line. And then that means we can use already this function in our code. as we do this in the main.rs in the kernel init function. We print out hello world text and call panic. By the way, panic handler also got some update, and what it does is basically the same. It's not just a loop, but also like printing some text out, informing us there was a kernel panic. So let's run the code, and when we call make QEMU, it builds the code, runs it. We see output text, hello world text, and panic message, because we called panic, if you remember, in the kernel init. If we won't call the kernel, it will be in the infinite mode, so it will like infinite waiting mode. I don't know how about you, but I was pretty excited to see this working and to see these first lines of the output text, because it's like first time in my life I trying to do something that seems and looks like so complicated, and I would be never able to do this, but it's a lot of fun. I still remember that it's not a true stdout. We will work on this and we will implement the stdout for real, but there should be a bunch of code before we implement stdout. But for now, it's like a really first steps, like writing some basic things, and next one will be another basic thing. So I will follow that tutorial, and there's a next step. It's writing lock system, basic mutex that controls who can write, read from the certain address, memory address. Mutex, basically, what we need. And this it's very important thing, and without this we won't be able to do anything else, because if we write drivers or we write like processes, virtual memories and so on, we need to care about who can write, who can't write. This locking is really important. Locking system will be in the next video. Please consider subscribing to see this and hit the like button if you like this. Thank you for watching and see you next time. Bye bye.